Thank you, everyone, for coming. I guess we're missing chairs. I don't know if there are chairs around. No, we're good. All right. Thank you, everyone, for coming. It's an honor to introduce Angela Schoellig. She's coming from the Institute of Aerospace Studies at the University of Toronto. She did her PhD at ETH with Raf D'Andrea, and then she's been a very productive and successful assistant professor at University of Toronto for the last 6 years, I think. Yeah. And she works on the connection between robotics, controls, and machine learning with an interest in performance guarantees and safety. And she has received lots of awards, so I don't think I have time to go through all of them. So I just picked one which I thought was interesting. She holds the Canada Chair on Machine Learning, Robotics, and Control, which has the name of a country on the name of the chair, so I presume that it must be important. Anyway, it's an honor to have you here, Angela. Thank you very much for coming.
Thanks. Thanks. Hi, welcome everybody. Can you hear me okay? So it's an honor to be here. I haven't been at MIT for some time. So what I thought I'm going to do for this talk is to give an overview of some of the ideas that we had. I could go into much more detail on all of these ideas, but this should give you a nice idea of how we combine machine learning and control for robotics. So we work with real robots, and we care about designing systems that have high performance. So here we fly 25 of these vehicles, in a coordinated way, and we want high performance here means, nice coordinated motions. And this was recently accepted at ICRA, and if you come to ICRA, it's nominated for multi-robot best paper, which is nice. We also care about reliability. This is a recent project where we use stereo vision as a backup for GPS. So we fly based on GPS, but if GPS, when we lose GPS, we could use the images that the vehicle captured during flight to safely fly back based on vision alone. And so here we fly up to 55 kilometers per hour, and we did tests even downtown Montreal earlier in the summer. So reliability is important in robotics. The same for safety. Here you see an off-road vehicle that we drive at our location. And we do right now a long-term experiment where the robot needs to drive this route as fast as possible, in every season. And in Toronto, as you can imagine here, it's the same as here. We have lots of weather changes. And we recently started a self-driving undergraduate team that competes in the General Motors AutoDrive challenge. It's over 3 years, inspired by some of the DARPA challenges. And so we had only 6 months to build the first prototype of this car, and we tested in winter conditions in Toronto, but the competition was in the desert in Arizona. So robustness, practical robustness is important, so systems working in various conditions. So that's kind of the setup of the lab. So if you come to the lab, you could actually see those systems running. And what is really interesting in robotics is compared to computers and smartphones that clearly have completely disrupted our work and personal life. Robots promise physical interaction, and that can mean moving people and moving sensors in the three-dimensional space, but it could also mean real physical interaction with a human during work tasks or helping humans in their daily tasks. But while computers and smartphones really operate in the virtual world of data and information, robots interact with the real world, and that makes the whole problem so much more difficult. So it's really an exponentially increasing complexity. How we have dealt with this in the past is that we built dedicated environments for robots where we reduced the complexity and where we could generate models that reflect the real world. However, the applications that I showed you that we aim to build as roboticists are aimed to work in human-centered environments where we have lots of prior uncertainty that is hard to model and describe. So while in a dedicated environment, we can build these nice building blocks from perception to action and hand engineer and hierarchy, manually program the robot, and use a priori knowledge that's sufficiently correct to make the robot work and do the tasks. In human-centered environments, our understanding is limited, and that limits the performance of the robot. And to give you a fundamental question that describes this problem is, how do we design robot algorithms that achieve safe, reliable, high-performance robot behavior in a priori unknown, unpredictable, and changing conditions? And one situation that we encountered in Toronto, if we do off-road driving over a longer period of time, a robot experiences all these different road conditions. So from light snow in January to freezing rain, then it got a little warmer, and we have sunny temperatures all the way to when the vegetation grows in May. So that's a range of different conditions, which is challenging both for the vision side, but also for the control. So to make a robot operate in all these different conditions, there are one way to do that, which is called robust algorithms. So if we design an algorithm that works just for all of these conditions. But as you can imagine, with the robot applications we have in mind, there's the range of conditions the robot has to work in is so large that robust algorithms ultimately turn into very conservative algorithms. So probably this robot would, drive extremely slowly because that's what it needs to do when we have heavy snow or ice. But in summer, we could drive much better, or in dry and sunny conditions. So a robust algorithm is never optimal for a single condition. And that's also called the robustness performance trade-off. And to deal with that in practical applications, our belief is that we need to enable robots to learn and adapt to achieve high performance in those uncertain conditions. So if you compare machine learning with robot learning, which is something that I try to just motivate, is that in general machine learning, we look at feed-forward pipelines, versus in robotics, we have dynamic systems and feedback loops. So we have sensors that measure the environment, and then based on the actual sensor reading, we act. So instead of an example like this, a typical feed-forward pipeline where I have an input image, and I want to answer the question, what objects are in the image? Is there an airplane, a person, a TV monitor? So it's a clearly open loop pipeline. The systems we look at in robotics perceive the environment, then decide what action to take next, and this action again influences what it sees in the next time step. So as actions influence the perception and vice versa, it is very difficult to have a complete data set a priori for these systems. So that's very different to some of the standard machine learning problems like object detection, but also even speech-to-text algorithms and things like that. On the other hand, general machine learning is not safety critical. If I don't detect the right object in its image, that is not necessarily a big problem. If my phone doesn't understand me, if I talk to it, I just try it again. It's usually not safety critical. But a robot doing the wrong actions could harm the environment and destroy the robot. On the other hand, we have usually unlimited data and computational power for these standard machine learning problems, but robots are resource constrained, and every time a robot moves in the real world, that is costs money. It's expensive, and the payload and communication of the robot is limited. But there are some other interesting features in robotics that make the problem interesting. So we can influence the learning. We can do things like active learning. We can, on purpose, move the robot in a certain location to gather data. And we know something about the physical world. There are physics laws that we believe are correct, and we should be able to incorporate in those algorithms. And often, there's more limited understanding of the underlying principles of some of the traditional problems that are solved with machine learning. So looking at all this together, there has been a lot of progress in robot learning. It's clear that people have shown that robots are able to learn new skills from experience. Often this has been done in these simulation environments. So here a virtual character learns to walk through reinforcement learning. These results have been limited often to learning single tasks and learning in very controlled environments, like in simulation or lab settings. And the learning components are placed in the closed loop, which means the perception module is used to decide what the next action is, and this is done in the closed loop. But safety is usually ensured through an external safety backup system. So a lot of the robot learning tasks that have been shown to be successful is in manipulation or using robot arms. And there, just the external safety mechanisms are used to make sure the robot doesn't harm itself or the environment. So really the open question is, how do we enable robot learning in realistic application scenarios outside of the lab? And for that, we need data-efficient algorithms, something I call online learning algorithms. So the robot needs to learn as it moves in the real world, because we assume we don't know the effects ahead of time that it is supposed to learn. And for that, we need to guarantee safety. And all of that is, as the robot moves in the real world, it's learning in a closed-loop system architecture. So it needs to perceive and then act, and perceive and act. And this closed-loop architecture, could cause systems to be unstable or fail if not designed properly. So really the question is, how do we bring robot learning to applications and out of the lab setting? Our approach in my lab has been to look at the combination of machine learning and control theory. That's the traditional approach to make machines do tasks on their own. And for me, control theory is the science of feedback. It's really the kind of the theory that describes feedback systems. So where I have a perception action loop that continuously runs on a system. And control theory has defined really important properties of feedback systems. For example, stability, performance, and robustness. These concepts are defined in control theory and are extremely important for any machine operating in the real world. So yeah, we have these action perception loops. In my group, we focus right now mostly on learning the right actions, assuming the robot has perceived its environment and has a good understanding of its own state and the state of the environment. What are the next actions to take? And we test on real robots, as I showed in the first videos. So let's see what we have been working on. So I structured kind of the approaches that we have been doing in 3 parts. Approaches where we leverage architecture and hierarchy. We have done some work on safe learning, and then some more recent work on the combination of really fast adaptation and long-term learning. So what are the particular problem statements that we look at? So the problem statement can be formulated in an abstract way like this. So a robot controller decides what next action to take based on what kind of a mission objective it should optimize for. So the mission objective really defines the task that the robot should be doing. And usually in a traditional control setup, these J functions are known ahead of time. And then we optimize over a horizon into the future So we decide what are the actions to take over the next n time steps to achieve my task. And then we resolve this optimization problem. We know where the robot is at the start, and we have a rough idea what the system dynamics are, and then state and input constraints can be properly incorporated. So this is a typical model predictive control framework, but you can think of it as a general framework of feedback control. And so if all of this is known, this is model predictive control and works really well. But in the real world, all of these things can be unknown. So I may know what the task of the robot is it should perform, but it may be difficult to formulate it in a functional form and write down these functions J. I may not know initially exactly where I am. I may not know how the system performs in the environment, like what I cannot predict based on an action and a state what the next state will be. And then the environment itself can be uncertain, so I may not know precisely where the obstacles are in the space, which could be encoded in state constraints. And if I have actuation failures, I may not understand exactly what actions I can actually perform with the robot. So all of this can be unknown, and then it's an incredibly hard problem. So my group has been focusing on this part, so on the fact that we don't know exactly how the system performs in the real world. So what are the dynamic equations that describe the robot's motion? And if you think of the robot that was driving on outdoors over a 4-month period, the unknown dynamics could be the slip and the interaction between the wheel and the ground that is varying a lot depending on the weather conditions. So if the ground is frozen, the system reacts very differently to if we have very muddy weather and lots of rain. So think of what we learn as the dynamics of the system. And then we approach this problem in different ways. And I just want to kind of highlight in the following how we combine ideas from control theory with machine learning, and where I think that, those two fields can complement each other. So if we look at architecture and hierarchy, control theory can help us to appropriately place the learning in the overall system architecture. So this includes choosing the right inputs and outputs of the learning module, deciding which part of the overall system is unknown and we need to learn. And it also helps us to distinguish systematic effects, which I can learn, from random effects. And random effects is something you have to cope with differently, usually with fast feedback. And control theory can also overall get us insight into the problem characteristics. And so one example is if you have a flying vehicle, a small quadrotor, a typical thing that we do with control theory is we have this cascaded loop of feedback controllers, where on the lowest level there is a motor controller that controls just the turn rate of the propeller. And then on a higher level, we close the loop to have for the vehicle to achieve a certain angle that we want it to achieve. And then on an even higher level, we have something like, we use GPS, and we have a desired position that the robot needs to go at, and then use a GPS measurement to actually control the vehicle to move to that position. And so we have this cascaded loop, steps of control loops. And we have a good understanding how the system works. And then we can, at the appropriate position, include the learning. And machine learning is especially powerful if there's repeatable input-output patterns that I can actually learn. So for example, at the lowest level, there's so much randomness. For example, if we would include the the machine learning right at the lowest level. There's so much randomness that it's really hard to learn. But if we close several of these feedback loops at a higher level, if you compare where should the robot be, the desired position, compared to where it actually is, and see the modeling errors that affect the position following, that's often a very repeatable pattern that we can observe. And there, machine learning can be very effective with very little data. So the interplay between control theory and machine learning here is the control theory can tell you where do I have the system, how do I close the loops, and where do I have systematic errors that I then can pretty easily learn with machine learning techniques. And so I show you 2 examples for that. So one was we wanted a flying vehicle to follow a desired trajectory. And we closed the feedback loop. And so we have a reference signal that represents the desired trajectory that the vehicle should fly. You will see it should fly a slalom trajectory. And then we see the actual output. And this system, from input to output, is very repeatable. So when I send the same reference signal, an hour later, I still get the same output, which is not perfectly tracking the desired reference trajectory. And so then we can put machine learning around and do the following. So we have a desired output behavior we want to achieve. We have an approximate model. In this case, we even assume we have roughly a model that describes what's happening in this dashed box, inside of this dashed box. And we have a parameterized control strategy. So again, this is also from controls. We have certain parameters that we choose to achieve the desired task YD. And then we run the system based on all our prior knowledge with our prior assumptions of what the correct parameters should be. We see how well the system does. So we see how close is the true output to the desired output. And then in this case, we actually just use this approximate model to tell us how to update the parameters to get closer to our desired behavior, so to reduce this delta y. And this is just a kind of an abstract formulation to give you an idea. So you can imagine if you, for example, play basketball and you throw a ball and it's not going far enough, you have an intuitive understanding that next time you have to push harder. And so this approximate model tells us something similar. So if we see what we did wrong in the first trial, the approximate model tells us roughly what to change in our parameters to get better next time. And so here we use control theory in many different places. So we use it to get this approximate model, to have an initial parameterized control strategy, and to close the inner loop such that we learn a repeated behavior. And then we can use that, for example, to learn a task that we couldn't do without learning. So if we did it without learning, just based on our prior knowledge, we want to fly the slalom as quickly as possible, this is what happened. But then we can start learning, and we learn here above the poles initially. And you can imagine from every time you do this task, you get more information about how the system behaves. And then we adapt those parameters and improve over time. And then after only 3 iterations, a very little number of iterations, we can actually do that task. And then we can learn different other configurations as well, like, for example, this forward flight. And we tested various configurations of those poles. And you can always learn them within 3 or 4 iterations because we put in a lot of prior information. So the lessons learned are we can modify this reference signal. And because of that, we don't jeopardize stability of the vehicle in the first place. As long as this reference signal is bounded, we have an underlying controller that makes sure the vehicle stays in the air. So the learning algorithm cannot kind of crash the vehicle. And because we use this gradient that was derived from this approximate model, the learning is extremely efficient because it tells us in which direction to correct the parameters to get better. And as long as the model is good enough to give us the right direction of correction, then this works extremely well. The limitations of this was we don't have really formal safety guarantees beyond stability because the formulation doesn't explicitly take into account state constraints. And each task needs to be learned again through repetition. We had some extensions on this work to work for formations of robots and also for periodic motions, but being in a similar fashion as this one. So from that, our next goal was, can we learn a model a priori from data that then improves any trajectory? And so we have, again, the same setup. And now we place this learning module in front of the, place it here at the beginning of the loop, outside of the baseline feedback controller. And the goal is that it learns an approximate inverse of this closed loop to have perfect tracking, so a desired output, a desired motion that I want to see of the robot, I see it perfectly done at the output. And from control theory, we actually know what this block should be. So if we do a simple analysis and we assume we don't know this dash green box perfectly, otherwise we would be done. But if we assume it could be either represented by a linear system or a nonlinear system, then we know what this block ideally should be. And those equations are written down here. And so they depend on two things: the state of the system, but also the desired trajectory are steps ahead. So we need to know something about the future of the task, what the task should, of the future of what we should do. And so control theory here can help us to decide what should be those inputs to those blocks. So what should be the input to this module that I want to learn? And R here is the relative degree, so it's the inherent delay of this underlying baseline system. And detecting what R is for a given system is very easy. You can just do one experiment, what is called a step response. For control theory, people know that very well. So from a step response, you can basically detect R. And step response, for people who don't know it, means if I have a flying vehicle, I just tell it, go somewhere else immediately, and you see how long it takes to react. And so this simple experiment can help us to design the inputs to the block that we want to learn. And initially, we didn't do the math. We just tried it out, and we learned this nonlinear approximation function from data. And after we done the math, we could reduce the number of necessary inputs to this. Here we use a deep neural network, but you could use any nonlinear regression technique. You could reduce the number of inputs significantly without jeopardizing the performance. And so the motivation and demonstration of this tool was anyone can draw something on a tablet, and the vehicle should try to follow this. And so here you see the red dashed line is the desired one, and what you just saw was a standard controller. And now you see how it improves if we just add this pre-block to the system. So usually we get an error reduction of 50% for every hand-drawn trajectory. And we tested this in the lab, and many people came and actually drew trajectories. And so it consistently reduces the tracking performance, and we continue to improve the system. So we actually have some recent accepted work at the European Control Conference where we further improved those results. But the main takeaway is we can simply put an add-on block to any stable black box system. So any black box controller that you buy, it may be your black box controller in your robotic arm that you don't even know what it is. Someone else implemented it. You just get this robotic arm, and you have some inputs that you can send, and you can observe the resulting performance. But by adding this block, you can improve that black box system, and it's task independent. So we learn this pre-block once from a range of training data. For the results I showed you, it's periodic motions, but it could be, we right now improve it by learning also from hand-drawn trajectories. And just adding this block, very simple, you can improve your performance. So probably anyone working with black box control systems could make use of that. And control theory here has helped us to improve the data efficiency. So we could reduce the number of inputs significantly from our initial work and still get equally good results. We also extended this work in various directions. For example, we can also learn this block, even so we know from theory this block would be unstable. So it's an inverse model learning for a non-minimum phase system. We can set up the system properly such that we learn a stable approximation of this unstable inverse. We also recently extended it to active learning. So we improve our learning process by deciding what trajectories to learn from. So after basically learning from a lot of periodic motions, you may wish to learn from some additional hand-drawn trajectories to further improve the overall learned approximation of the inverse. So these are two examples where we leveraged architecture and hierarchy in a relatively simple way by just placing the learning at a place where the system has systematic input-output errors, and then learn from very little data a correction that is significant. Another area that we have been working on is how can we make the learning process, if a robot learns in the real world, as you saw for the slalom learning, for example, the robot learns and adapts in the real world. How can we make this adaptation safe? And here, again, we combine ideas from control theory with ideas from machine learning. So control theory has provided definitions for stability and performance of uncertain systems, so systems we don't know well, and has developed methods that guarantee stability and performance for those systems. And one technique to prove stability of systems and also uncertain systems is something called Lyapunov theory. So we leverage those tools from control theory, and then we use machine learning to learn those uncertain, unknown effects. And with just making very weak continuity assumptions on the unknown effect itself and using probabilistic learning models, we can kind of provide a stochastic model of the uncertainty that then can be used in standard control theory. And to give you an example, what motivated us to do this work is we drive this off-road robot through the terrain, through narrow fence openings, through dense vegetation, close to buildings and infrastructure. And we want the robot to improve its driving speed over time, while never, of course, getting off the path too much and jeopardizing safety. So how can we provide these high probability safety guarantees? That's the best we can do. We cannot give 100% safety guarantees. We can give safety guarantees with high probability during the learning phase. And so the approach is using a probabilistic learning model that represents our current knowledge and belief of the unknown effects. And so the usual approach that we take is we combine our a priori model for ground vehicle, that could be a unicycle model, a simple kind of kinematic or dynamic model of the system, with an additional component that we just add to it that is learned. So if G is 0, we are all in our old domain, we know what's going on, and we can use standard methods. But if we have some unknown component, some friction component that's unknown, we want to learn that. And we hope that as we gather more information from the real system, that our understanding and our knowledge about this G gets better and better. And so once we have a good model of this system, we can use robust control theory that controls this uncertain system. So use probabilistic learning to describe our current knowledge of the system, including uncertainty bounds, and then use standard robust control to control the system. So how does this look like in detail? So for the probabilistic model, we use Gaussian processes. And so Gaussian processes are distributions over functions. So at the beginning, we may not know anything about our unknown model. And the safest thing to do is to say the function lies anywhere in this large blue shaded region. With only minor continuity assumptions, any of these colored lines could be the true function, but we don't know yet. So the blue shaded area is kind of our best understanding of what's going on. But then we gather data as the robot moves. Every time we move, so with our ground robot it's 50 times per second, we get a data point. And then at those inputs, so the current state and current input, we can measure our G, and we get a good understanding what's happening in this region of the input space. And so the uncertainty envelope shrinks in this at the points where we get data, the red points, but it also shrinks in between, and that's because of the kind of continuity assumptions that we make. We assume that a function cannot suddenly jump. So we learn also something in between. And now, for example, in this area, we have already a pretty good understanding that the function with high probability lies in these blue shaded areas. And a lot of our fundamental proofs that we do for this work go back to a result that was presented at ICML in 2010 that basically says that under the right weak assumptions, the true function value lies within this blue shaded area with high probability. And so we know basically that the blue shaded area, the confidence intervals of the Gaussian process, represent valid high probability bounds of the true function value. And so basically, with every data point we get, we shrink this blue envelope and we get a better understanding of the unknown system. And then we can combine it with something, for example, any robust control method, for example, model predictive control. So model predictive control makes decisions based on predictions about the future, and now we can use our learned model to make predictions. But you saw we have not a perfect knowledge about the learned model, so the predictions are still uncertain. And we don't know perfectly where we end up. And model predictive control has the other nice feature that we can include input and state constraints. And so here is a practical description of what is happening. So at a certain position, the robot looks into the future and tries to optimize its actions over the next period or over the next period of time, for example, a prediction horizon of 10 seconds. And now we have this learned model. Just going back, we don't perfectly know how the robot behaves, but we know it behaves somewhere within this blue shaded area. And so since we don't know exactly what the robot does, for a given fixed input sequence, the robot could possibly end up anywhere in this shaded red area with high probability. And so that may mean that over this horizon, it violates the path constraints. Obviously, given that we want to enforce input and state constraints, what the algorithm would do is it would reduce the speed, and therefore it wouldn't get as far over the prediction horizon, but over this horizon we would make sure that the robot stays within the fixed path bounds. And so what is implicitly here encoded is that at slower speeds, usually our models are more accurate. And we can make sure that with high probability we stay within these path bounds. But then as we gather more data over the learning process, and this is a continuous process, so whenever we get a new measurement, we can update our model and use this updated model in the decision-making process. So as we get more data, this envelope shrinks, and that means over the prediction horizon, I'm more certain what's happening with this robot. And I can drive faster while still staying within the path bounds with high probability. And so this approach is very generic. It basically combines a stochastic modeling approach with robust model predictive control. And if we apply it to a robot.
Can you tell us how you're rolling out the uncertainty distributions?
Yes, okay. Let me stop this. Yeah, so what you would need, even if you know perfectly where you are at the current moment, then you have a model that is stochastic. So even if you apply one input, you don't know exactly where you end up next. It could be a variation. So we use a sigma point transformation. So we basically approximate it as a Gaussian. Yeah. But that runs fast enough. And it's a good approximation for our system as we've tested in experiments. And so then here you see side by side driving an off-road trip. And you see when on the left, when the robot drives this path the first time, and then on the right when it drives it the third time. And you see that it can significantly increase the speed. And you see the uncertainty envelope is smaller, and especially on straight paths, the system learns very quickly, and as a result can drive much faster. I hope you can see it. So we did actually significant tests with this. So this is off-road, just outside of our building, and so the particular section of the path is finished much faster once you have done it a couple of times. And intuitively, it's if you drive in a city the first time, you're probably also driving very carefully. But then as you do it multiple times, you gather experience. You know how the road, the kind of way the road goes, and you can drive much more confidently. And that's basically what is happening here. We did significant tests of this because we had industrial partners. So we tested this on a planetary rover of the Canadian Space Agency as well, in more of a planetary mock-up setup in Montreal. And we also tested this on a vehicle from the Defense Research and Development Canada. And again, very different vehicles. The only thing we really modified were some of the hyperparameters of the Gaussian process. very mildly, and in every situation the vehicle could learn from the data it gathers. So this provides high probability safety guarantees. In practice, what it meant is we could drive this vehicle off-road faster than we would ever feel comfortable otherwise. It would also naturally slow down in turns, because that's where our vision system also doesn't work. So the vision system would give a larger uncertainty, and so naturally would slow down. The nice thing was also that we can, in real time, incorporate data. And for some time, this was the most downloaded paper on IJRR. And it also led to some other developments that could be talks on their own. So we developed a safe model-based reinforcement learning approach, where we safely update the policy to guarantee stability, versus the typical approach to reinforcement learning, which is kind of randomly trial and error. This kind of carefully decides on the policies to guarantee stability at all times. We also used Gaussian processes in a different setting, in a more model-free reinforcement learning approach to directly optimize controller parameters safely. And so this type of approach has actually also been used. I show you a video on flying vehicles, but it also has been used by Google to optimize the cooling of their data centers. This was developed separately by Google, and the Google approach has a few more approximations. But the idea is that we try out only controller parameters that are safe. And so here you see kind of the idea. So a very simple setup problem to illustrate the idea. We have two controller parameters. We want to optimize the performance on a given task, flying from left to right as quickly as possible. So that defines our performance metric. But we don't know how the controller parameters map to a performance value. So think of a PID controller, and you want to do a certain task with your robot. You don't know ahead of time which controller parameters work best for the given task. And so here, it optimizes it safely. And under the assumptions that we make, we find the safe global optimum. So it tries it several iterations. Eventually, it finds the safe global optimum and gets a controller that is optimized for a given task. So this was a simple illustration. It also relies on Gaussian processes and the model-free approach to directly learn this mapping between controller parameters and performance. So overall, the safe approach, yeah.
Can you tell us how you're getting this high probability correctness, given that you have a Gaussian approximation? I understand that you're bound the GP approximation, but if you're rolling out with just a Gaussian approximation, that seems hard to balance.
Yeah, so for the model predictive, you are talking about the model predictive part. Yeah, so there it's harder. Without some additional assumptions, it's hard to do any proofs. So there it's kind of inspired by our formal analysis. That's our safe model-based reinforcement learning paper, but then it's kind of the practical implementation of it. So it's hard to prove really formally what's happening if you assume nonlinear systems, Gaussian processes, and so on. We don't have a full proof of exactly the setup that we have in the experiments, only of a simplified version. For the automatic tuning, we do have, yeah. So these are some first approaches towards safe learning, but the idea is don't try randomly actions and learn about the behavior of the system in the real world, but try actions that guarantee you a certain amount of safety, which could either be what control theorists would call stability. So I just want to guarantee the vehicle doesn't crash, or it means I really stay within the path bounds or within some other state constraints. And then the last part I just want to briefly touch upon. I think it's really important, and something that we have been working on over the past few months is how do we combine fast adaptation, which is something that the best thing, if something randomly happens that's unexpected, the best is to quickly adapt. So let's assume you have this off-road robot driving, and there's a patch of ice. I mean, the best is to use very fast feedback to react quickly to this unexpected behavior and somehow try to correct it. But then there's also the long-term learning. So if I see, snowy roads again, I'd like to learn from last year's winter and use those results. And so we have done some first approaches in this direction, where we use very fast adaptive underlying feedback to very quickly correct for those unknown, unexpected conditions. And so 2 approaches that we have been exploring is using L1 adaptive control or really fast Bayesian linear regression. And then in the long term, use that data to collect experience. And again, this is probably something that we humans do as well. We very quickly react if something sudden happens, but then we also long term get better at driving or get better at a certain task. And I just want to kind of give you a glimpse into 2 different ways. So one is where we use an underlying L1 adaptive controller. So an adaptive controller that very quickly corrects for model errors and tries to make systems behave like a reference model. And so we use that underlying adaptive controller with a high-level iterative learning approach, similar to what you saw in the Slalom Learning. And what you see here is we look at either a standard underlying controller, a PD or PID controller, or this L1 adaptive control approach. And so we learn a certain task, think of it the slalom, and then over iterations we get better. But then we suddenly switch to a different vehicle, which is a sudden change, different dynamics, and that usually would mean that I need to relearn this task on this different dynamic system. But if I have this underlying L1 adaptive controller that compensates for these dynamic changes very quickly, I can actually reuse the knowledge that I collected with this other vehicle. So L1 adaptive control or any other adaptive control can help to quickly compensate for dynamic differences, and then we can, on top, do some high-level learning, and this kind of architecture allows us to even transition knowledge between different systems. Another approach, okay. I think I skipped this. We have a very recent paper that we are presenting at ICRA, so if you're coming to ICRA, we basically do fast adaptation with Bayesian linear regression and then some long-term learning on top of that. So to summarize, there is an interesting kind of connection between machine learning and control theory, where control theory is really the science that allowed us to understand these type of feedback systems, and it allows us to do online and data-efficient learning on real robots with high probability safety guarantees in some respect. The disadvantage is we put in some additional structure. The architecture that I showed you are human designed, so we don't know, is there a better way even for systems to learn? But overall, the structure that we put in can allow us to learn very efficiently on real robots without making very strong assumption about the unknown effects themselves. So whenever we kind of did this approach, we kind of fall back to methods that don't make strong assumptions about the things we don't know. For example, we use Gaussian processes, a very, very generic stochastic modeling approach. We eventually work with quite a lot of different collaborators to apply this technology in different fields. And in the long term, it's just something I'd like to kind of put out there for all of you. I think in robotics, we, on the one hand, have to deal with increasingly more challenging environments, from static environments like a factory floor to much more dynamic environments, as well as we want robots to do increasingly more complex tasks. And then, you could map the different applications that you can envision robots to do on that kind of grid. And for example, the universal household robot would be very challenging. It's a complex task that it needs to do, but also very challenging in dynamic environments. And I think to kind of get there, we need learning and adaptation. We probably need advances in many different other fields, including sensing and actuation. But we don't get there without prior knowledge. And so I tried to kind of plot the results that we have been doing in this kind of coordinate frame. And we have, whenever you have sufficient information, that's the easiest. That's where most of our real applications lie. But then dealing with increasingly more dynamic environments or more interactive and human-centered complex tasks is really challenging. But I think it's needed to kind of eventually get to the point where we have a seamless interaction between robotic systems and the physical world. And I think there's lots of open questions, but we try to show that there is some hope that we can have safe adaptation of robots in the real world. Thanks.
Any questions?
So thanks for the talk. I guess my question was, how would we apply this in like a manipulation context? I sort of see two big challenges. One is XT is not something that's known, especially when you're interacting with objects, especially if it's a novel object, what is the state? Second of all, I think GMM models are challenging here because if I just think about a contact dynamic, it's super discontinuous right at the contact boundary. So do you have any thoughts on how to address those two challenges?
Yeah. Overall, yes, we try to make first steps in this in the direction of safe online data efficient learning. Discontinuities would not, cannot be captured by the Gaussian process ideas that we had. Some of the other iterative learning techniques could possibly do that, but it's still, I think, it's a very open and challenging, interesting problem. Yes. I think we just did, from the model-based techniques, a little step towards something else, but there are so many open questions if you talk about interactions. Yeah.
Thank you for a fascinating talk. The last part, machines changed from one type of machines to next machines, but the L1 conveyed most of the stuff to the next one, so very quick convergence. I'm just wondering, what the specific physical part of the model is conveyed? For instance, from 4 rotors to 6 rotors, can you change that? Any kind of prior knowledge must be embedded into that?
Yeah, so we have, this is an interesting question. Basically, how similar do systems have to be to do this kind of knowledge transfer? And so we have, it's a question that I'm thinking about for a long time. So even towards the end of my PhD, I have some results in certain contexts. I think it's generally still an open question. Like how similar do systems have to be to actually work? Or also this adaptive control assumes a reference model, and which reference models are appropriate for which class of system. Yeah, I don't have. Oh, I'm sorry. I don't have a formal. There is no. I think, at least to the best of my knowledge, there's no clear answer to this. If people do that, even this is a relevant question. Even if you learn in simulation and go to the real world, when does it work and how well does it work? It depends on how close the simulation is to the real world, and I think nobody has really characterized how similar this has to be, or You can imagine if it's perfect, identical, then it works, of course. And if it's slightly different, it degrades, but how well? So we have we kind of try to think about this in different contexts. A recent paper that will be presented at ICRA, we also kind of have this similarity argument in there and try to mathematically characterize it a bit better. But I think overall there's no clear answer. Yeah. Thanks.
Hey, Professor, thank you for the talk. I have a question about the safe learning. Could you go back to the slides you have on the safe learning part?
Okay.
In there, one of your model is that you added the error or the
Oh, yeah.
uncertainties to your dynamic
Okay.
equation.
Oh, sorry, I was just flipping back. That's maybe the easiest. Yeah.
Oh yes. So right, so
This
this one. So I understand why you're adding the error linearly to the dynamic equation, but in the real world, there's a lot of cases where your signal comes too fast or too slow. Can be for both control and observations. So therefore, I'm wondering, have you ever tried any experiment or any insight to add those noise directly to the xt and then the mu t instead of put it outside?
Yeah, so adding this in an additive way is an approximation. We have, what I should say is that we have explored that that G does not only depend on X and U, but other variables or a history of those variables. So we explored that, but we always kept it as an additive term. I think more from simplicity and because we didn't see a strong case to do it differently, but I think that's again a way, if you have a good understanding of your system and you know where those uncertainties enter, then you can adapt this, this equation and probably get more data efficient learning, right? The more understanding you have of where the uncertainty is, the less data you would need. But we haven't tried that, yeah. Yeah, I'm sorry for being late.
Okay, thank you. So within your safe model predictive control, do you have any step that your control actions lead to gathering more data from the system other than just robust control? For example, in your adaptive control, it just reminds me of persistent excitation that you need to make decisions that lead to more data from the system to do it better.
So, yeah. In the model predictive control work that I showed you with the vehicles driving, is kind of implicitly embedded in the cost function because we want to, the cost function encourages the vehicle to drive faster. And so whenever we have a better model, we drive faster, then we learn more about that part of the state space. So it's kind of implicitly encoded in the cost function, but not in as much of a formal way. Basically, we still, even in the model predictive control case where we learn this part, right, this model, in some way we only learn it in the state space that we operate in, that we need to operate in based on our cost function that we define, yeah. We don't really have any explicit way to eventually learn the full model. That's different if you go and look at the safe model-based reinforcement work published at NIPS. There we look at a much more simplified stability case, and there we guarantee that we have an explicit exploration as part of that as well. Yeah.